In this presentation, I'd like to talk to you about product substitution. We hear a lot about product substitution in forests, but it's based on a number of key assumptions that are rarely discussed. So I'd like to go over those with you today, give you a little more understanding of what you need to consider when thinking about product substitution. The key points of the talk are that substitution of wood for other building materials has the potential to have a positive greenhouse gas impact. But the degree that that potential is realized depends on the degree that the displacement value, that is the amount of carbon that's displaced by the use of wood, changes over time, whether that fossil carbon is used by other sectors, the degree that substitution actually occurs, and also the system that's supplying the wood. Before we get into the meat of the talk, let's talk about what the forest sector is. It's the forest ecosystem, including the live plants and carbon, the dead plants and carbon stored in those, and the soil. Then there are the wood products that come from carbon harvested from the forest. Some of that is in use, and some of that is disposed, say in landfills. Then there are substitutions of products and energy. And we also have other sectors that could interact with the forest sector, for example, the transportation sector, the energy sector. This creates a hierarchical system. We start with the live, creates dead and soil. That's the forest ecosystem. We harvest products and they store. Their use can create substitutions. And then we have other sectors that might also use fossil carbon that sort of intersect this system. So that's what we're talking about, a hierarchical system in which we have multiple parts interacting. Now let's start with a standard product substitution story that you read in newspapers and even in articles, scientific articles. These are the general points that are covered, not necessarily in this order. So we have wood-based building materials that require less fossil energy to produce than concrete, steel, brick, or other materials. Therefore, using wood-based building materials releases less carbon dioxide to the atmosphere. We have an added bonus in that wood-based materials also store carbon, and wood is a sustainable, renewable resource and hence carbon neutral. So anything we do in the substitution arena will just accumulate carbon. Now, behind those statements are a number of assumptions which are rarely covered even in scientific articles. The first is that the displacement factor is constant over time. It never changes, despite changes in efficiencies and sources of fossil carbon. The fossil carbon that's not used in the building sector or to build buildings is never used by any other sector. Preferences for materials are unchanging, with concrete and steel always preferred. And finally, the harvest of wood cannot reduce the store of carbon in a forest at the landscape level. By that I mean multiple stands of different ages which are harvested at different times. And one stand is offsetting the effects of another with regard to exchange with the atmosphere and carbon. If we take those assumptions, we get the classic product substitution story. And you can see down below I have the website in which this was taken from. I think the conclusion is pretty clear from the website title. But anyways, we have the various pools that I described, the forest itself and dead wood, products, etc., and substitution. And we see substitution is an ever-increasing store through time. It just keeps growing up as a straight line function. And Indeed, by the time, say, 100 years at the end of the simulation, it's as large as anything. In fact, it's the largest store. It's over half the store in substitution. Now, this outcome is based on several assumptions that generally aren't described. In fact, many of the papers, even in the scientific literature, do not specify the assumptions that are made. So let's go through some of these one by one. The first question I have to ask is, why wouldn't the displacement factor change? For example, the manufacturing process could become more carbon efficient. Say we replace coal with natural gas, or maybe the process itself becomes more efficient. For a given amount of energy, you produce more product. Also, non-fossil based energy could be used to make many of these non-wood products. So to understand the effect of that, we need to look into the displacement factor. What is it exactly? And it's the amount of carbon not used per unit of product substitution. And mathematically, we can have the displacement factor, dF. It's the amount of fossil carbon in the non-wood material minus that in wood, divided by the difference in the amount of wood used. Now, it seems weird that in the non-wood building we use wood, but all buildings use wood to some degree. So by wood we mean primarily wood, and by non-wood we mean primarily non-wood. Okay, so mathematically we can simplify that. I know that's a lot. Let's just assume we have 1 unit difference between the wood and the non-wood. So it really becomes the difference between the amount of fossil carbon that's used. In the equation, we have 3 minus 1. Suppose, for example, non-wood used 3 megagrams of carbon in its manufacture, and the wood used 1. The difference would be 2. Okay, so let's say that we change the efficiency of both, or we change the fossil source, say from coal to natural gas. That would reduce the amounts in half. So we'd have 1.5 minus 0.5, that equals 1. So that has an impact on the displacement factor. Now the equation in red down below is not what the displacement factor is, but it's what most people think it is. They think it's the ratio of non-wood to wood. It's not that, it's the difference. And so if you change the efficiency, if it's a ratio, the displacement factor doesn't change. So some would argue the displacement factor can't change, but actually that's based on the wrong mathematics. It can definitely change. So what happens if we do change it? And here's a series of simulations in which we reduce the displacement factor 25% in the red tones, 50% in the blue tones, and 100% in the purple tones, which would mean that basically we totally get off of fossil energy. And what we see is that has a big impact on the amount of product substitution we accumulate over time. And as we drive down that displacement factor, it gets lower. And there's also an effect of the timing. You know, 25 years has a greater effect than, say, 100 years. But the primary effect is how much we drive it down. So that assumption that it's constant seems kind of dubious, and it has a big effect. Let's change assumptions now. Let's look at what happens to that fossil carbon that isn't used in producing wood. And the assumption is that it stays in the ground. In some cases, authors have actually written that once the displacement occurs, the carbon stays in the ground forever. But does it? The current rates of fossil carbon depletion range between about 1% and 4% per year. depending on the form of fossil fuel. Coal has a lower rate than gas and oil, but these are actually significant rates. Now, many countries have decreased or tried to decrease their fossil carbon use. So you would think that the amount of fossil carbon emissions to the atmosphere would go down, but they haven't gone down. And that's because energy demand keeps increasing. So different regions like Southeast Asia are using the fossil carbon now, whereas Europe is using less. This is a classic leakage scenario. So to know that the fossil carbon is not used, you need to know it's still there. And that in turn depends on what it is and where it is. In general, when people talk about product substitution, they don't tell us what form of fossil carbon it is, and they don't tell us where it is. And in part, that's because this is unknowable. What happens if that displaced carbon is used? This shows different leakage amounts or timings from 25 years to 800 years. So the numbers I gave earlier were like 50 to say 200. This would be the red dashed line to the blue dashed line. That would have a significant effect on product substitution. But even if it took 800 years for that carbon to leak out, it still would have a big impact. So this is another untenable assumption that actually has a very major impact on the substitution value. Now let's turn to maybe the more complex, the most complex of all of them, and that is the relationship between substitution and building longevity. Essentially, it assumes that there is no relationship, but there must be, because decisions on the materials that are used occur when a building is replaced, which means there must be some relationship there to longevity. And if we have a scenario in which wooden buildings are replaced by wooden buildings, then you have to ask, is a substitution occurring? I would say not. Let's consider some facts. In North America, 95% of residential buildings are wood-based. The majority of North American studies on product substitution have dealt with residential buildings. So what is going on? How could there have been a substitution? Well, this seems to assume that the preference for wood suddenly reduces to zero. But why would that be? And it also ignores the fact that preferences for building materials can evolve over time. That is, perhaps concrete and steel is used now, but in the future, people prefer to use wood-based materials. Let's look at the relationship if we tie the product substitution to the lifespan of buildings. And we go from 25 years to 200 years, and then the black line, which is as if buildings had an infinite lifespan. And I say as if because they actually act that way even if they don't have an infinite lifespan. So what we see is even if the buildings lasted 200 years on average, and this actually means that there are buildings that exceed 200 years, we would have a significant decrease in the product substitution value. In actual buildings in North America, it's probably more like 50 to 100 years, somewhere in that range for the average lifespan, and that has a very large effect. So again, this assumption is very critical and has a huge impact on what we see in terms of the substitution accumulation. So that was each factor one by one. Let's combine them. The red lines are buildings that have a 50-year lifespan, the blue 100-year, and then I have some in which we assume that buildings have an infinite lifespan. That's shown in yellow. And then I've varied the leakage term and also the timing of the displacement and how it decreases over time. We see that for the majority of the simulations, we actually have very, very little product substitution accumulating. And the yellow lines are all ones in which there's an infinite lifespan. I think that's a dubious assumption. And they also assume that things like leakage are very, very low. That is, it takes 800 years, when in reality, it's going to be less than 200 years for that fossil carbon to be fully used and depleted. So at the very least, this suggests that there's huge uncertainty in product substitution values because we don't necessarily know many of these things, and that the past assumptions are overly generous. In fact, what they really are the assumptions that would give you the maximum theoretical product substitution value. And while that's a useful number, it's not what's really going to go on. Now, let's turn our attention not to those assumptions about the product substitution, but to the effect of the wood source. And we could get wood from several different systems. One, it could be a forest that was created by agricultural conversion. We planted on an abandoned field, put a forest, and then we started harvesting it. Or in the upper right, we had a sustainable plantation in which we've been harvesting for some time, and we continue to harvest, and it doesn't drive down the store of the ecosystem when we do that. Or in the lower left, we have an old growth conversion in which we take a large store and we decrease it. In each of these graphs, we see a red line, and that's the initial value or store of all the ecosystem shown in blue, the product shown in purple, and then the substitution in black. And there's two substitution lines. The dashed line has some set of assumptions of a decline in the displacement factor, a leakage that occurs over a 300-year period, and then a 75-year-old house or average house lifespan. And the solid black line shows the assumptions that are currently being used. Well, we see huge differences in each one of these cases between the current substitution assumptions and what we might call more reasonable assumptions. So if you use the current substitution values, the only way to accumulate carbon is to actually do the timber harvest and substitute. It creates a huge store of carbon, of fossil carbon that isn't used. But if we use the assumptions that are more reasonable, we see that some situations, like the ag conversion, lead to an accumulation of carbon. The sustainable plantation doesn't really accumulate much carbon at all. And the old growth conversion, while it has an initial increase, eventually leads to a decrease in stores. So the current assumptions mean that whatever we do, from wherever we do it, we end up with a huge substitution store. But more reasonable assumptions lead to a sensitivity to where we start from. Now, on the lower right, I've looked at old growth conversion, and I've changed a whole bunch of assumptions just to give you a sense of how sensitive it is to these. So the baseline is the curve on the left, with the new assumptions about product substitution. The purple line is if we increase the building lifespan twofold, from 75 to 100 years. The black dashed line is what if we eliminated leakage? We made sure that the carbon wasn't used. What if we doubled the harvest interval? That's the solid black line. What if we decreased the displacement value? So what we see is that they all have some minor effect, but the real effect is driven by what the source of the wood is. And old growth conversions are generally going to lead to a carbon loss over time. Now, these are at the landscape level, and that explains why the old growth conversion has a slight increase, because the initial stands are accumulating product substitution values, and we haven't really affected a lot of the stands. But as we've got to get into about half of the stands, we see it switches to negative. So when we convert the whole landscape over to the plantation system, we end up losing carbon over time. So I have a few conclusions. The first is that product substitution is highly uncertain. There may be some of it going on, but unless we look at the assumptions and have a greater understanding of what's going on, it could be high and it could be low. We really have no way of knowing. If you modify any of the assumptions, it's unlikely to be as high as commonly presented. And if we take the most likely scenarios, it's probably at least less than half, and it could even be as low as 2% of what's commonly being presented today. To make credible estimates of product substitution, you need to do a few things. You need to project how the displacement factor will change over time. You need to create a system in which the unused fossil carbon remains unused. Nobody has really been discussing that. That's critical. It has to remain unused. And we also have to account for changes in material preferences. They aren't constants, and we can't start with one set of preferences and switch them to the other because it gives us a higher substitution value. Or likewise, we can't do the other. We have to start with what it is, and then we need to see how it might change over time. And finally, we need to know what kind of system is actually supplying the wood. Without that, we really cannot tell what the effect on the atmosphere is going to be. This turns out to be a very critical assumption, and one that perhaps we could do a better system of actually tracing where the wood comes from so we understand the carbon impacts. Thank you.